So as a passionate researcher in nanotechnologies in catalysis, environmentals, and smart materials, she published around 82 ISI index papers with 72% of the publication as corresponding author as well as first authors. So furthermore, she's composed an academic book entitled Nano Catalyst in Environmental Applications in year 2018, which is published by Springers, as well as 8 chapters of books and 20 conference proceedings. So it leads through her a latest H index of 25 with the citations of 2,752. So today, Dr. Laily's sharing topic is focused on the applications of metal oxides hybrid photocatalysts in water treatment. So Dr. Laily, can you share with us about the major issues on the recent trends of the water treatment approaches and how the photocatalyst technology may change the paradigm? The stage is yours, Dr. Laily.
Okay, can we start again? Okay, first of all, I would like to thank Mr. Chairman, Dr. Lee, for the introduction about myself as well as my research background. And I would like to thank the JRS Sustainability Webinar for these invitations. Okay, come back again to your questions. Let me share the slides to make it much more clear. Okay. So come back to your question, Dr. Lee, about the water crisis and why it is important for us to tackle the issues recently. So I will highlight here a few statistical data about the water issues globally. So if we can see that half of the world populations, they are suffer from the polluted water, whereby as a Malaysians, one of the developing countries, 70% of the developing countries, the waste from the water are not treated well. So it comes from the urbanization, from the industrialization, even it comes also, the waste are come from the agriculture activities. And 1 in 9 people in the world, they don't have any access to the improved source of the drinking water. And 1 in 3 lack or to improve sanitations. And the water-related disease is one of the disease, one of the top disease that kill, that are very harmful to the children. And 2 million people are still lack to access of the safe and the sustainable supply of the fresh water. So this is the scary data here. So it will motivate us to develop the innovative way to for the water to degrade the persistent water pollutants. Currently, we have several numbers of the treatment system, especially the associated with the nanoparticle. For example, we have the membrane filtrations, the sand filtrations, the chlorinations, iodine, hydrogen peroxide ozonations, and also the biological treatments. However, these treatments normally associated with some limitations that make them not fully treat the pollutants. For example, for the membrane filtrations, it's only transfer the pollutant from one area to another area without fully degrade it. And then for example, another example for the biological treatments, so it need a long of the incubation time. Especially when they are dealing with the nitro or the benzene compound. And another example for the limitation of this system, for example, we consider about the chlorination or iodine. So they need they have the storage issues, and some of them because of the it are toxic to humans and need high dose of the compound, and it will definitely affect the total cost of the water treatment. And if we consider about the ozonation, so these ozonation treatments, they need a strong oxidize that may cause to the hydroponic mineral nutrient to the participate. and also it will affect the viability of the system. So at this point, simple, effective, less cost, and also environmental friendly water treatments needed. Here, in the 1950s, there are some scientists from Japanese named Fujimas have introduced about the photocatalytic water purification works. So the basic principle of these photocatalytic water purification works, they are using a light to activate the semiconductors. Normally it's nanoparticles, okay? And these start with the activations of, and this process is considered sustainable treatment, since it has ability to completely mineralize the water pollutant without producing any secondary pollutants. So the basic principle of this photocatalytic water purification system, so it has a 4 stage. So the first stage starts from the absorptions or diffusions of the water pollutants on the surface of the semiconductor. Okay, so there are several parameters that we could consider to make sure that this process, the absorption or the diffusion process, can achieve effectively, just as the pH of the polluted water, the concentration of the pollutions, and also the dosage of the catalyst or the semiconductor. Then after the absorptions, so the light or the photon of light will be introduced on the surface of the semiconductor. So here, the electron from the valence band of the semiconductor will get excited and jump to the conduction band, leave the hole. So this electron and hole pair will be responsible for the oxidations and the reductions of the water pollutants. And this process is considered environmental friendly if the reaction will carry out under the solar radiations. So, and the catalyst will be automatically deactivate after this oxidation and reduction process completes. And it can be reused and recycled for several numbers of times. And that's why here this is considered as the cost-effective water treatments. There are several numbers of the metal oxide semiconductor that considered to be a good photocatalyst on the degradation of different type of water pollutants, just as the iron oxide, titanium oxide, tungsten, zinc oxide, and so on. But the most common one is the titanium oxide, because the titanium oxide is the less toxic. It's much more cheaper other than compared to the other semiconductor. And most importantly, the titanium oxide doesn't have any problem on the dissolution of any solution or media as compared to the other semiconductor. It's stable, so it can be used at a different pH of solutions. So thank you, Dr. Lee.
Okay, thank you, Dr. Laili. So thanks for providing this overview of the photocatalysis systems. So I hope that all these can motivate the scholars who wish to learn more about the green and sustainability of the catalysis. So especially in these treatments of water contaminants. And Dr. Laili, and the second question here. So what's the motivations and the purpose of using metal oxide as the photocatalyst in your study? What is the efficiency of this developed catalyst in water treatments, and as well as to assure that the full mineralizations of the water contaminants without any secondaries of pollution formations?
Okay, thank you, Dr. Lee, for the question. So the main objective of the photocatalyst system here is, compared to other conventional method, is we are looking for the more green technology, which is not only transfer the physical water pollutants to another part, but it also can be degrade completely to the less harmful molecules. Okay, so the motivation of this study is we will look more on the advantage of photocatalysis system for the water treatment, as I have highlighted before. So the advantage on the photocatalyst we can have in the wide spectrum of organic contaminant may be degrade. So here, they have a possibility for us to degrade of a different type of the water contaminant in organic or organic. For example, from the clinical waste, from the agricultural waste, herbicide, pesticides, synthetic dye, and so on. So it can be used for the universal type of the water pollutants. Then it can be regeneration, since that most of the photocatalytic are in the heterogeneous catalyst, which is in the solid form. So it can be separate at the end of the treatment system, and it can be regenerate and be reused at the several numbers of times at the maintained reactivity efficiency. And then the reaction only if this is a mild condition reaction. So the reaction is only take place at the room temperature and pressure. So we don't need any high temperature or any pressure to assist or to catalyze the reactions. And it can be applied on the both on the slurry or the immobilized reactor. So it's a flexible setup of the reactions and no need for the post-process. Means that it's a one-stop reaction. So normally, it will no need to combine the treatment with the other other water treatment. Okay, and the last one is about the reuse of the photocatalyst and the consumption of expensive oxidation chemical. So what is just need is only the semiconductor, the light source, and the water for the reaction to be happens. And for here, we are using the titanium oxide due to the several advantages. And one of them is the high oxidation efficiency, and it's a non-toxic. So this is the green technology and the great absorption. Why we need the high absorption efficiency for the photocatalyst? So then we can only use a small amount of catalyst for the high concentrated of pollutants. And it also have a chemical inertness and environmental friendly use, low cost, and is stable in terms of the mechanical, thermal, and chemical, and have a binding affinity then for the absorption of the water pollutants, and is a practical. But there are some limitation of the titanium oxide. Okay, so then the first one is on the utilization of visible light. So we want the treatment system to be available under the solar radiations. Okay, because for example, in Malaysia, we receive amount of the solar light radiation every day. So to get used this system into the solar system, so we have to do some modification because the titanium oxide band energy, the band gap energy for the titanium oxide to be photoactive is only 3.2 eV, means that it's only active under the UV light. But the UV light only consists of 5% from the solar light, and 45% for the solar light is under the visible light. So here is our responsible to change the band gap energy of the TiO2 might be under 3.2 eV to make sure that it can be applicable under the sunlight radiations. The next one is the high electron hole recombination rate. So this is happen in the crystalline light of crystalline side of the TiO2. So and it will make the system is not stable at the long period time of the treatment. And it also had a lot absorption for the organic pollutants. So some modification need to do on the surface of the TiO2 to make sure that it can absorb more organic pollutant with different active surface. And according to the nanoparticle, as everyone knows, when we reduce the particle size of the metal oxide or any type of material, so the surface area will increase and the activation of the catalyst will be increased correspondingly. But we have some problem about the aggregations, means that the nanoparticle tend to agglomerate in its nano-size dimensions. And the last one is difficulty in the discovery of nanoparticles, since it is in a nanoparticle, so it's the filtration, the common filtration system are not able to discover the type of the nano dimension materials. And the poor thermal stability, because it's the anatase, the crystalline of the Nano2, which is responsible for photocatalysis in the anatase, has a poor thermal properties. So our job here is how we can tackle all these 6 limitations and make sure that the TL2 titanium oxide will become a promising semiconductor for photocatalysis system in degrading or in mitigations of different types of water pollutants. So there are some strategy or treatments that have been done by previous studies. For example, the metal deposition, doping by metal and non-metal element, the carbon-based material loading, heterostructure, dispersion on support, and so on. And this system have the advantage and the advantage, but not any single system can tackle all these 6 limitations. They have the advantage, for example, it can enhance the electron hole separations, mean that it can be stable under the long period of the treatment. Some of them, it can be improve the light absorptions of the semiconductor into the visible range. But it also has some limitation in terms of the metal leachings, the recombination contour, and as well as the separation at the end of treatment system. So here, by taking notes on all these advantage and disadvantage of these modifications strategy, we can come out with a ternary system of the photocatalyst. Here, the combination of the we are using titanium oxide with the other metal oxide or the sulfide will improve the band gap, will reduce the band gap energy of the semiconductor and make it applicable under the visible light. But they have some limitation. For example, under the photoradiation, so there will be the electron diffusions between both of the metal oxide or the metal sulfide. So in order to overcome this, we introduce the passive layer of the chitosan between this metal oxide. Okay, this passive layer is the non-semiconductor. So here we consider about the chitosan. So chitosan is come from the natural sources. So the chitosan will be a linker between these 2 metal oxides. Other than that, since chitosan consists of the numerous or plenty of the amino and also the hydroxyl group, so it will assist on the absorptions of the semiconductor or the photocatalyst and make sure that the maximum or the high equivalent of the water pollutant will be absorbed on the surface of the catalyst. And that chitosan also responsible to support the catalyst reactions to make it have a homogeneous distributions along the way of the treatment system. And also, since the nanoparticle is in the since the semiconductor in the nano dimensions, so the chitosan will make sure that the separation will be the good separation will be occur at the end of the treatments. Thank you, Dr. Lee.
Okay, thank you, Dr. Laili. So now we know that this is the several important criteria to be taken note to design and synthesize the efficient and durable hybrid types of metal oxide-based photocatalysts, especially to reduce the limitations on this titanium photocatalyst, right? And it is exciting to know more about your research findings on the developed metal oxide hybrid photocatalyst. So can you share with us more about your research finding in these relevant studies?
Okay, thank you, Dr. Lee, for the question. Okay, in our lab in the Nanomaterials Research Center, so we have developed a series of the metal oxide hybrid support chitosan photocatalyst. For example, we start with the titanium oxide with the zinc oxide. We also have the titanium oxide with copper oxide coupled with the chitosan and also zirconia. So all the system based on the material characteristic in terms of the crystallinity, in terms of the light absorption sensitivity, particle size, or the band gap evaluation, and also the porosity, it found that they have a good promising catalyst system for different type of the water pollutant, for example, for the clinical waste, pharmaceutical residues, synthetic dye, and so on. But for today's presentations, okay, so I will present about one of the system that have been developed by our lab members. Okay, in this system, we introduce the ternary, which means that it's composed of the 3 different elements in the catalyst system. The TiO2 as the main catalyst, and then we incorporate with the iron oxide to reduce the band gap energy. The heterostructures between the formation of heterostructure between the titanium oxide and the iron oxide will be reduced due to this hybrid system, and make it applicable under the with the band gap under the 3 EV. And then, in addition of iron oxide, not only reduce the band gap of the TiO2, but it also introduce some magnetic properties to the composite. So at the end of the catalyst reactions, the nanoparticle could be easily separate from the system by the magnetic bar. And here the chitosan, the third element, will introduce as the linker between the iron oxide and TiO2. And chitosan will also, due to the presence of the functional group of the amino and hydroxy group, chitosan also can be as the to be the absorption site for more water pollutant to be absorbed in the catalyst system. So we hypothesize that this system will overcome the 6 limitations of the TiO2, the catalyst, photocatalyst for the water treatment in terms of absorption, in terms of the white light sensitivity, and in terms of the regeneration of the catalyst. So for that, we have developed the system and tried with photocatalytic to the nitrophenol water pollutants. And this is nitrophenol compound is one of the most persistent water compound, most toxic, from the industrial wastewater. So it has been used for the manufacturing of fuels, on the agriculture, for the industrial wastewater, and it has the effect of the carcinogenic, the highly toxic. And also it's about 190 tons for phenolic waste is disposed monthly. So as considered to these facts, so the nitrophenol have been selected as the model for our water pollutant in this ternary photocatalyst system. So here, why is chitosan? Because previously people are using other materials as the supporting materials, such as the silica, graphene, carbon, and so on. But this type of the support system, they doesn't have a good absorption property as been expected. And most of them are non-toxic and doesn't have the antimicrobial activity as the chitosan concerns. Okay, so there are several research questions that we will answer for this project. For example, how to improve the activity of the in the visible regions to make sure that we will get you 45% of the light radiation under our normal sunlight, and how to make it stable with a stable catalyst to reduce the recombination of electron hole pair, and how to make sure that this system will be recovered, the photocatalyst, after water treatment, and how many times that this catalyst can be reused and recycled with the maintained photocatalytic activity. The methodology is simple. We play around with the molar ratio of the precursor, the iron, and also the TiO2, and by using the Soldier methods. And the material, the produced catalyst, will be characterized in terms of their physical, chemicals, and also morphology properties. And the photocatalytic activity will be done with the respect to the reduction of the nitrophenol under the UV light as well under the solar radiations. So this is some important micrograph image that we taken from the scanning electron microscope as well as the transmission electron, and it shows that the TiO2 are fully covered the iron oxide core, and the chitosan will be a linker between these two metal oxides. And the comparative covering of the TiO2 shell over this iron oxide chitosans shell to form a well-defined core shell structures. From the TEM, the lattice fringes for both metal oxide are clearly observed for the iron oxide and also for the TiO2 at their respective d-spacing. And from that, we can calculate the particle size of the composite of these three elements are around 24 nanometers. So for the physical properties, so it shows that the coating of the chitosan to the iron oxide core will increase its crystallite size. So the combination of these three elements have the high crystallite size, which is it will reduce the band gap of the TiO2 as well as the towards lower than 3.0. So for the we study as well the photosensitive absorptions of this hybrid system, and it showed that the low peak intensity indicate a better charge separations. So mean that this system have good stable electron hole recombination system as compared to the pure TiO2, which is a main requirement for the good photocatalytic performance, especially if we concern it to be used under the sustainable solar light radiations. And this is the reduction is happened due to the formation of the heterostructures and the coupling of these two metal oxides, the TiO2 and also the titanium oxide and iron oxide, which is it can lead to the increase in the charge separations and increase the transport and decrease the rate of recommendations, make the system will be stable over the period of the catalytic process. So the band gap has been reduced. For example, for the pure TiO2, the band gap recorded is around 3.19, and as the ternary system has been introduced, so the band gap reduced down to below than 3, which is 2.65. So the pearl objective of this study has been achieved by reduction of the band gap and make the system applicable under the solar light radiations. So this is the functional group of the to ensure that the chitosan will be a good linker between these two metal oxides. The formation of the amino acid and hydroxy stretching for the FTIR analysis is obviously observed for the respective wavelength, and it shows that the three elements has been a good composed between each other. So as we expected, because TiO2 and chitosan is non-magnetic material, so addition of these two elements into the iron oxide will significantly reduce the magnetism properties of iron oxide, but it still be considerable since the reduction is not really significant. Okay, so the magnetic property of iron oxide reduced with the addition of iron oxide, the TiO2 shell and chitosan coating. So this result shows that and show that the hybrid system has been successful fabricated. So let me share to you the photocatalytic activity, how these catalysts, how these three elements can be a good promising photocatalyst for treatment of the nitrophenol. So for the degradations reactions, there are several parameters that we are consider. The first one, the catalyst loading, and for that, and also the second parameter that we consider on the nitrophenol concentrations, several ppm has been considered from 30 to 50 ppm, and also the pH of the solution. So here we consider for the acidic and up to the base solutions. Okay, so from the result, so it shows that the high catalytic degradation increase, the degradation of the nitrophenol increase with the catalyst loading, but up to the 0.3 gram, so it start the catalyst, the nanoparticles start to be agglomerate, and this agglomeration will result on the limit light penetrations, and subsequently it will hinder the peroxide generation of catalytic surface and reduce the catalytic properties of the system. And because of that, when we introduce the more amount of the water pollutant of nitrophenol, so the high absorption of nitrophenol on the catalyst surface will be increased, and then it will achieve the saturated or the equivalent stage, whereby the photon formation become difficult and consequently deactive the catalyst surface. And from the perspective of the pH, so it shows that around the pH 6, that it will have the best photocatalytic or the optimum photocatalytic performer will perform at the pH 6. After pH 6, for example, for the base medium, so it starts to be deprotonations of the OH group in the cytosine, which is it will be reduced the ability to be attacked by the hydroxide. This sample have been up to, so the for the degradations performed up to 92% of degradation under the visible light radiations. So it's considered good as compared to the titanium oxide itself is only can achieve around 72%. I try to. Is it my slide moving, Dr. Lee?
No.
No. Yeah, no. Maybe you can remove the slide and then
Yeah,
start
maybe you
again,
have to.
exit, and then just for the slide. And share again.
From the bottom left.
Okay. Is it moving?
Yes.
Yes.
Okay. So in order to know that it's a completely degrade or completely mineralized by the under this photocatalytic system, so we have done the total organic compound analysis. Okay, so it shows that almost 60% of the OMP or the nitrophenol have been degraded to the harmful to the non-toxic or less harmful substance. The irradiation time increased with the presence of the TOC or the total organic compound removal, and also increased until it reached to its maximum removal efficiency, 81% after 3 hours of the reactions under the visible light radiation. So we can see that this system can completely degrade up to 81 to 90% of this persistent water pollutants, which is a nitrophenol, under the visible light within the 3 hours of reactions. And in terms of the recycle or reusability of this system, so the efficiency is maintained up to the 4 times of the cycle. So this is because the good interactions between the 3 elements in the hybrid system, and which is sustain the morphology, optical, the physical, light absorption properties during the series of this degradation process. So we propose how the degradations or the pathway of the nitrophenol and what are the intermediate compound that produce along this degradation process. So 2 reactions has been considered here, which is the hydrosylations and the dinitrations. On the hydrosylation, so the first one, the nitrophenol will go for the denitration first before it goes to the hydrosylations. In the hydrosylations, the hydroxyl group addition occur to the aromatic ring of the ONP and lead to the formation of the carbonic compound and carboxylic acids due to the ring cleavage. For the denitrations, it indicates 60 minutes with the less nitro group at the aromatic sites. So here we confirm that by the GC analysis that the HPLC analysis that the phenolic group of the carbonic and the phenolic group of the nitrophenol has been less down or has been reduced during the reaction process of the photoreductions. Thank you, Dr. Lee.
Okay, thank you, Dr. Laili. It's very interesting findings about this synergistic effect of the hybrid type of catalyst, photocatalyst. So our final concern here is about the challenge on the photocatalysis technology. What is the difficulties and your viewpoint to immerse the photocatalysis in the conventional water treatment system? Thanks.
Okay, thank you, Dr. Lee. So we are researchers. Normally we develop everything. We try to solve the problem in the laboratory scales, but there's still a challenge or there's still some limitation for us to apply our finding or our inventions in the big scale, for example, for industry scale, and can be used for the public. So that's the same thing goes with the photocatalyst water treatment system. So because it has been developed 16 years ago, but it's still not be commercialized yet by for any system because there are some challenges or limitations associated with this treatment. Okay, the first one that I think that is important on the photoreactor setup. Okay, so because here there are several parameters that we should consider to make sure to not only to develop a highly efficient catalyst, but also to make sure that the catalyst is fully utilized. The catalytic of the photocatalyst is fully utilized during the reactions. So there are some parameters that should consider, for example, for the light source, for the synthesis, the characteristic of the catalyst itself, and also the medium medium of the water pollutants. So for that, there are some considerations that should be in mind when you want to develop or you want to commercialize the system. The first one on the distribution of the pollutant and the photocatalyst. You have to make sure that there are some maximum interaction between these two, the pollutant and the photocatalyst. The pollutant can be completely absorbed by the catalyst at different concentration medium. And also the pollutant mass transfers, how the transformation of the pollutant into the catalyst surface. The reaction kinetic should be considered as well because the reaction is taking in the microseconds. So we need to make sure that we have produced a highly stable catalyst with the high rate of the reactions. Also the irradiation characteristic, how the position of the light, how it can and the for example the distance between the light and also the catalyst it is also important to be considered to make sure that the absorption of the light is completely absorbed by the catalyst and the amount of treated water, okay, and the surface of the catalyst. And this one is normally associated with when we consider the nano dimension of catalyst. And lastly, the uniform distribution across the area. So the normal setup for the photocatalytic reactor is the batch photocatalytic reactor that normally we have in the lab. But this setup associated with some limitation and difficult for the scale up. And then for the low process throughput and the operational is complexity, because it only can be used for the single parameters or the single reactions. So that's why the some researchers come out with the new continuous photocatalytic reactor, which is much more easy for the scale up and have the high throughput, simple operations, and it can be reused and recycled. The catalyst can be reused and recycled many times. And the energy, and it also can save in terms of the energy efficiency. And here the setup is focused on the catalyst that being dispersed on the slurry or it became immobilized over the support. So the next challenge on the photocatalytic parameters. So there's numbers of parameters that normally we will consider in running the photocatalytic activity. For example, the type of suspended metals, the ion temperature, pH, and the organic matters. So these parameters should be optimized in order to have a good phase composition, electronic structure, particle size, expose of surface area, degree of aggregation, mobility, charge carriers, and so that, and it needs to be optimized to make sure the absorption of molecule, light scattering, and photoabsorption will be optimized to get the best catalytic reaction process. And for that, some improvement will be should be highlighted in terms of generation of the long lifetime reactive species and the interactions of the pollutant with your photocatalyst system. Means that the surface of your photocatalyst system need to be manipulated to make sure that it will have a good interactions with the type of your targeted water pollutants. And the last one is on the toxicity. When you are talking about nanomaterial, you cannot run away on the toxicity of issues. So most of them, as the particle size reduced, so there are some concern on the toxicity. So that's why a detailed toxicity assessment should be considered or should be reported and be published in the public before it can be commercialized. For example, before the treatment system, during the treatment system, and after the treatment system. So this detailed toxicity assessment will include how the photodegradation of the organic pollutant, the wastewater detoxification, how the reuse of the catalyst, and how the mineralization of the pollutant will be performed during the catalytic system. With that, I think these three elements or these three factors is a big challenge for the photocatalytic system to be commercialized in our real life. Thank you, Dr. Lee.
Thank you, Dr. Laili. So thank you again for your very insightful presentations, Dr. Laili. And I know that there are a lot of challenges and opportunities on this roadmap of photocatalysis developments, especially in these water treatments and remediations. So it is believed that the continuous research studies and modifications will make it realized in the future. So we hope the best success for you, Dr. Laili.
Dr. Lee, before we go for the Q&A, I would like to ask your permission as the chairperson to maybe 5 seconds to give some brief introduction about NanoCat Research Center.
Yeah, I think we still have time to have some short briefing about this NanoCat.
Okay.
Right.
Okay.
Thanks.
So this is only 5 seconds. So the only one slide I prepare for the introduction for the NanoCat Research Center. NanoCat Research Center is one of the center of excellence that in University Malaya, Malaysia. So we start from 2001 until 2020, and we are we also one of the national center of excellence Malaysia. So our focus area on the catalyst design, which we use for the nanocatalyst, nanomagnetite. The nanomagnetite is some of the examples that are present today. For the nanocarbon material covering from the carbon nanotube, graphene oxide, radium graphene oxide, and also semiconducting oxides, the nanocellulose, and also the carbon nitride. Okay, we also, from this, the catalyst design, it will apply for the different type of the application for the smart materials, the chemical catalysis, for example, for the synthesis of the antioxidant itself, and also functionalize of nanocellulose, the pyrolysis, leading to value-added chemical and so on. And also used for the energy catalysis, okay, for the hydrogen production, fuel cell, solar cell, and so on. And as one of the topic I present here, environmental catalysis. So we use our nanomaterial or nanocatalyst for the mitigation of the water pollutants, for the nanofibrations, and also the to disrupting of other micropollutants, just as pathogen and so on. So if you guys want to know more about the details on the about the centers, so we have 10 numbers of the academic staff in the centers that dedicate for the research work, and you can go on this website. Okay, thank you, Dr. Lee.
Okay, thank you, Dr. Laili. So ladies and gentlemen, now offers the floor for questions and answers. So if anyone who wish to ask questions or share some thoughts and opinions on this relevant subject is welcome to raise it here. And you can channel your questions and comment in the chat box or Q&A box here, or as well as the live mode. You're welcome to share your questions here. Thank you.
Okay.
Yeah, I think they need some warm-up sections here. So maybe I'm the first to ask simple questions to Dr. Laili. As you mentioned that your hybrid system type of photocatalyst is kind of can make sure and promise the durability during the water treatment, right? Can you share with me how actually the process to confirm the reusabilities on the durabilities of your catalyst in this application?
Okay, thank you, Dr. Lee. Okay, so one of the objectives for this research work is we want to fabricate the catalyst that can be that can maintain the photocatalytic activity as well as the maintain its other physical optical properties. So for that, we have run several we call it the recycling or reusability of the catalyst in the several numbers of runs, means that after the photocatalytic activity will be run for 160 minutes, 3 hours. And at the end of the reactions, it will be collected by the magnetic bar. And it will wash and and regenerate, and it will be reused for the second run and afterwards. So from our data, it shows that the degradation efficiency maintained up to the 90%. Even after 4 numbers of runnings. So means that the properties of the catalyst is durable for the long period of the time and numbers of the reuse process. So this is due to the formation of strong interactions between the iron oxide, these two iron oxide, and the chitosan itself. And that's why the morphology, the optical characteristics, all has been sustained or maintained during the degradation process. And it can be, and this data can effectively shows that the catalyst can be utilized for the treatment of the wastewater at the low cost and at the sustainable approach, because we don't have to synthesis, or we don't have to produce the new catalyst for every time of the reactions. So it can be reused, and it can be reused with the maintained properties with only the simple separations method and reuse method.
Thank you. We have a questions from the floor from
Okay.
this Lee. Thank you for comprehensive presentations. How will the applications in pilot studies? Moreover, In water treatment plant which operates for 24 hours continuously, should it operate differently at days and night? And how is the comparisons between using the solar radiations and the artificial UV lights?
Okay, so to answer the first question, I think they have three questions here. The first one, how we can implement into our real water treatment or the current water treatments. Okay, this system can be standalone treatment, or it can be combined with the other treatment. For example, we can combine with the filtration or nano filtration to remove first the suspended solids, and then it continues with the photocatalytic activities for the water aqueous water solutions. Okay, and then the second question is about what the difference between you to apply this system under the real sunlight radiations as well with the artificial solar irradiations, right? So our sunlight radiation is not only composed of the visible light. It's also composed of the other different type of light, the visibles, the microwaves, and so on at different wavelength. So we cannot, if only 45% of the sunlight that composed of the visible light. So the efficiency of this system under the visible light as compared to the artificial visible light, which is 100% of visible light. So the efficiency is much more effective with the artificial visible light as compared to the sunlight due to the portions of the visible light under the sunlight radiations. And the third one is is it the
questions? So
Day and night.
yeah,
Operate differently during daytime and nighttime.
or during the time, the 24 hours. So we don't have to go for 24 hours if we can treat the water for 3 hours. Well, if we can short the treatment system up to the 3 hour, why we should go for 24 hours? So I think this is in terms of the efficiency. It's not in terms, the system is on the efficiency and to reduce the cost of the reactions. It's not about the if we can treat the same amount or the same volume of water for the 3 hours. So I think it and completely mineralize all the water pollutant into the harmless compound. So we don't have 24, we don't need to longer durations to achieve the same result.
that means the system can be applied either in batch mode or continuous mode, right? So it is very efficient. It can be
it depends on the reactor setup, whether it's a batch or the continuous reactor setup.
Okay, thank you, Dr. Laili. So yeah, okay, yeah, thank you also from this Welly, the participants. And yeah, any more questions before we end this webinar?
I think Dr. Laili has given a very comprehensive illustration about the study. So if the audience has any thoughts about the study, please also feel free to let us know. Or if you don't want to type, you can also raise your hand, and using the raise hand button down the down the WebEx window.
Okay, if I can respond back to these questions, because I go for the methodology that we apply in our research work, that we do the photo reactions under the visible light of an LED spotlight. We only use the LED spotlight with only 30 watt. So this 30 watt LED spotlight will give you up to 95% degradation of the nitrophenol compound. So can you imagine if we increase the watt of the light, so or with the comprehensive setup of the reactor, so I believe that the more efficient result will come out. And we also test the system under the UV light as well, whereby we only use 150 ml of the solutions under the 95 watt of the dermoside light. And it can achieve up to the 70% of the reductions on this persistent water pollutant of nitrophenol. If this system can degrade the highly persistent water pollutant, I believe that this system also can be used for the simple compound of pollutants. Okay, so for example, the metal ions and so on. So this is to respond to the light sensitivity questions that be raised by the audience. Do we have any more, Madeline?
Yeah, I think now there's a comments from the participants that you have an amazing presentation. Okay, congratulations, Dr. Levy. Yeah. So in this case, shall we end the sections, Michelle?
Yeah, sure.
For another
in case I think that's the end of the section, but if for the audience, if you can think of any question that you would like to ask both the speaker or the chair, please send your question to satu@ncke.edu.tw.